So for example 5, we're going to solve the inhomogeneous differential equation y double prime plus 3y prime plus 2y is equal to sine of e to the t. And let me remind you that we solved the homogeneous equation for this one in the previous example. So let me bring you up to date with what we learned from example 4 here. And if you haven't looked at example 4 recently, just go back and read that over so that this won't be a complete mystery. Example 4 told us that the homogeneous solution to this equation was C1 e to the negative t plus C2 e to the negative 2t. So that was our y1, and that was our y2, and we already found the Wronskian of those, which turned out to be negative e to the negative 3t. So we're in pretty good shape to get started on the inhomogeneous equation here, which means we're going to use variation of parameters. So using our formulas for variation of parameters, u1 prime is negative y2 times g over the Wronskian. So negative y2 is negative e to the negative 2t. G is sine of e to the t. Remember, g is whatever you see on the right-hand side there. So sine of e to the t. Got that over here from g of t. And our Wronskian matrix is, our Wronskian determinant is negative e to the negative 3t. So this does simplify a bit. First, of course, the two negatives cancel each other. And this e to the negative 3t, if you bring it up into the numerator, it becomes e to the positive 3t. And so you have e to the positive 3t, e to the negative 2t, just gives you e to the 1t times sine of e to the t. So that simplifies a bit. To get u1 itself, that was just the derivative we found there. We need to integrate e to the t times sine of e to the t dt. And we're going to do a little substitution there. We're going to do a little s substitution. So s is equal to, I can't use u. Normally I like to use u for u substitutions, but we're already using the u's for something else here. So I'm going to pick another variable, and I picked s. S is equal to e to the t, and ds is going to be, well, derivative of e to the t is just e to the t dt. And so here I have sine of s, and this e to the t dt just gives me a ds. And so the integral of sine s is negative cosine s, which is negative cosine of e to the t. So that was just a little substitution. It might be worth reviewing the Calculus 1 lectures for substitution here on Educator.com if you're a little rusty on how to make substitutions in integration. Let me show you the next step is to figure out u2 prime. Again, using the formulas from the beginning, we have this is y1g over the Wronskian determinant. Now our y1 was e to the negative t. G is still sine of e to the t. And we're dividing that by negative e to the negative 3t. That's the Wronskian determinant. And so if I simplify that a bit, I'll pull the negative outside, and I will get e to the negative 3t when it comes up into the numerator turns into e to the positive 3t. So we got e to the positive 3t and e to the negative t. That gives us e to the 2t times sine of e to the t. And that was just u2 prime. To get u2, I have to integrate that. So u2 is the integral of that. I'll pull the negative outside. So e to the 2t times sine of e to the t dt. And we can solve this one using the same substitution. I'll get my s is e to the t, ds is e to the t dt. And so this part will give me a sine of s. And now this e to the 2t, I'm going to write that as e to the t times e to the t. And the reason I'm doing that is I need one e to the t for my ds. So if I take one e to the t to be ds, those sort of collectively give me my ds. I still have one e to the t left over, so there's still an s left over there. And so I'm integrating s sine s ds. And that's still a little ugly. I'm going to use integration by parts here. That was something we covered in the Calc 2 lectures here on Educator.com, so you can check back and look up your material on integration by parts if you're a little bit rusty on that. But I'm going to do the quick version. The integral of s sine s. I'm going to use tabular integration here. I'm going to write derivatives on the left. The derivative of s is 1. The derivative of 1 is 0. And the integral of sine s is negative cosine s. And the integral of cosine s is sine, so it's the integral of negative cosine s is negative sine s. And then I make little diagonal lines, put a plus and a minus. And so what I get here, I still have this one negative from the outside. And then I'm going to read along the diagonal lines there. So negative s cosine s plus, because we got a couple minuses there that cancel each other, sine s. And if I distribute my negative back in, oh, by the way, remember we don't have to include the c when we're integrating to get these u's. So that's one nice thing you don't need to worry about. If I distribute my negative back in, I'll get positive s cosine s, and let's remember that s was e to the t. So e to the t times cosine of e to the t, negative sine s, because there was a negative on the outside, negative sine of e to the t. So that's my u2 there. So now I've found u1 and I've found u2. I'm ready to just plug them in to the generic form for my particular solution, which, let's remember, is it always has the form u1 y1 plus u2 y2. So u1 excuse me, is negative cosine e to the t, or sorry, that was y1, so let me look up, oh yes, u1 was negative cosine e to the t, and that gets multiplied by y1, which is e to the negative t, plus u2 is e to the t cosine of e to the t minus sine of e to the t. And all of that gets multiplied by y2, which was e to the negative 2t. And what happens here, if I distribute that e to the negative 2t here, e to the negative 2t times e to the t is e to the negative t times cosine of e to the t. And so I've got e to the negative t cosine of e to the t here. I'm not forgetting that other term. We'll get to that in a second. But over here, we've got negative cosine e to the t times e to the negative t. So those two terms cancel each other out. This is pretty common in variation of parameters. You'll get two terms that cancel each other out in some funny way. It's not always obvious why that happens, but it's nice when it does. So the only term I have left here is coming from these two terms, or these two factors. So minus e to the negative 2t times sine of e to the t is the way it simplifies down there. So that's my particular solution. My general solution, remember, is the homogeneous solution plus the particular solution. And so that's the homogeneous solution we already figured out back in example 4 was e to the negative t plus c2 e to the negative 2t. And now I'm going to add on the particular solution that we just worked out. That's negative So minus e to the negative 2t sine of e to the t. And so that's my general solution. Since I don't have initial conditions, I don't need to figure out what C1 and C2 are. Remember, you don't put a constant on the particular solution, just on the homogeneous solution. And so that's my general solution, and I'm done with that one. Let me recap what we did there. We started out with the homogeneous solution, which we found from example 4. So if that was a mystery where that came from, go back and watch the video for example 4 again. You'll see where that comes from. Read off y1 and y2 there. And we had also figured out the Wronskian matrix in the previous example. So that's still coming from example 4. So we had our Wronskian there. And then we use our formulas for u1 prime and u2 prime in terms of y1 and the Wronskian matrix and y2. And also there's a g in there, and we get the g from the right-hand side of the original differential equations. That's where that g comes from, here and here. We simplify those down. That gives us u1 prime and u2 prime. And then to get u1 and u2 themselves, you have to integrate those. So that's what we're doing here, is we're integrating with a little substitution. First one wasn't a bad integral, just to get u1 by itself. Remember, you don't have to add a constant when you're doing these integrals to find u1 and u2. u2 was a little messier. We had to integrate this, and so we did a substitution first, and then even after substituting, we had an integral that we needed to solve by integration by parts. And so that's what I was doing up here. This little table is doing the integration by parts to integrate s sine s. If that's fuzzy for you, you might want to go back and check the lectures for Calculus 2 here on Educator.com. There's a whole lecture on integration by parts where you get some practice with that. And so after we did that integration by parts, we got to here, substitute back and distribute the negative sign, s is e to the t, and we got our u2. And then we took u1 and u2 and plugged them into our generic form for the particular solution. So there's our u1 and u2. Multiply them by y1 and y2, and it was nice because some terms canceled. That term canceled with that term, and so it simplified down to a single term here. So that was our particular solution. And then to find the general solution, remember you add the particular solution back to your homogeneous solution. So there's our homogeneous solution again, and there's our particular solution being added onto it. So that's how variation of parameters works, and that's the end of this lecture in the differential equation series. Again, I'm very happy that you're watching. My name is Will Murray, and you're watching Educator.com. Thanks for joining us. Bye-bye.